Good morning, 8th and ninth grade, or maybe it's afternoon. I'm not sure when you're doing this science lesson. I hope you get all your work done in the morning. I don't know if you can or not. If you can't, I've got one answer. I got a solution of how you can. If you're needing to work into the afternoon, you're not being able to complete everything before lunch, there's only one way to get that done. And that is not work harder or faster, it starts sooner. So you have to get up earlier to start. Okay? That's my bit of advice for you this morning. Anyway, we're in science and it kind of feels funny here. We did a lesson, then we did tests, and now we're going back again. That's my fault. I didn't have those tests out there for the week before. I got to think ahead, and sometimes I don't, but I'm trying to now. Anyhow, I thought we would do review. If you open your book, turn back to the first part of our unit on Model 14 on sound waves. Waves and sound. There we go. I should have said the title correctly. We are still talking about electromagnetic waves. And now we talk about the different types of waves. And I will give you just a quick little rundown. When we talk about a wavelength, which is going to be everything, let me give you some basics. A wavelength is from the top point to the top point. That's a wavelength. Okay, it's got the crest. No, it's got the trough and the crest. And wavelength is from the top of the crest to the top of the next crest. And these wavelengths can be stretched out, or like we talked about earlier, they can be pushed together. So you can have them real close and they can be tall, or they can just be long and stretched out. Everything is in proportion. If you make them real close together, they're going to go tall. And if you make them far apart, they're going to be stretched out and not very high. Okay? Everything is directly in proportion. The longer the wave, the flatter it is. Does that make sense? The higher the wave, the shorter it is. I don't know if I said that right or not. Yes, I did. Sometimes I gotta think myself. And then we have what? Oh yeah, we have this symbol. This symbol that is called, let me see, it's on the bottom of page 342, or second to the last. It's a Greek letter, and it's called lambda, is the way I'm saying it. It's lambda, so I'm saying lambda. This lambda stands for hertz, or it stands for frequency. And so that brings me to the next point of this. This is review, okay? This is review, so let me step out of the way here. For frequency, that's F. And for the speed, that there is in seconds, meters per second. And then the hertz, or the wavelength. Here, I put length here. I just abbreviated this. This is still on 342, so you can find that. You see, the reason I'm telling you this is necessary information for future use, okay? So I thought I just had to go back and brush up on this here. So to find a frequency, which I'm imagining that Mr. Lyle talked about frequency a lot. Now, if he didn't, he should have. Frequency has the speed and the length. And so what you need to do is divide the length into the speed to get your frequency. Okay, so it's important to put the length on top. No, the speed on top and the length on the bottom, and divide the bottom into the top, and that will equal frequency. Now it tells you in the lesson you need to be sure that you have it in meters per second. And that will tell you, now let me back up here and tell you what frequency tells you. Frequency tells you how many of these wavelengths hit you every second. Okay? If you see a frequency of 25, I don't even know where that number comes from, it just popped out of my head. If you see that frequency hitting you, you know that every second, 25 wavelengths hit you. If you're standing in the room and the waves are hitting and you can hear it, or if you turn your ear like this here, you can 25 of them hit that per second. That's frequency. How many of you did the experiments? I caught you. I just had this little feeling nobody would do the experiments. I got a deal though. If you have done the experiments, when you're ready to, by the time you're ready to do or watch this video, if you've done the experiment, one or the other, there was 2 experiments. If you did either one of them, on page 345, the whole page is experiment, even, and then there's 2 of them there, and then on 347, there's another one. If you've done, there would be 3 of them that you could do. If you've done one of those, you call me or text me, and I have a surprise for you. You will get rewarded for doing your experiment. Okay, I need to review this yet. This is also, if you are talking about figuring out the speed of sound in air, is just a little math problem, because the warmer the air, the faster the speed travels of sound. The waves travel faster through the air if it's warm than if it's cold. Now, I don't know exactly how to explain that, but what happens is they can vibrate quicker. The waves go faster. So what you have to use is you can just about not see that, can you, on your screen? It's 3, and this is an example in book. You should actually, if you want to see, it's 14.2 example on page 348. I talked about this the other day, and you should have done some problems like this. You will do some problems like this on a little sheet of paper that I'll hand out at the end of this model. Okay? So you need to know how to do this. It's not hard. It's very easy. Matter of fact, of all the algebra problems you've done, this is one of the easier ones. They're just about like finding the frequency. You need to 331.5. You just need to rivet that in your head. 331.5, 331.5, 331 and a half. I don't care how you remember it, but whatever it is that number plus, okay, this is in parentheses, 0.6 and the Celsius temperature. You cannot use Fahrenheit, okay? If it's Fahrenheit, it will not work. So you have to have the Celsius temperature, multiply it times 0.6. This is a multiplication sign. Multiply it times 0.6 Celsius temperature. That's the end of the equation, okay? Not further. And once you go 0.6 times Celsius, then you add it to 31.5. Multiply first, add to 331.5. There we go. I missed the 3. 331.5. So you do a multiplication problem and an addition problem. Is that hard? Not really. Okay, turn your books. I'm ready to start, I think. Oh, it gives you a little example too about how to figure thunder. I always thought that every second was 1 mile, and that's not true. Every second is a 1/5 of a mile. So if it's 5 seconds, you know the thunder's a mile away. All right. On page 351, I'm ready to start today's lesson. That all before was just review because of the long time, which has been about a week, I guess, if you did this lesson last Thursday. Now we have today the speed of sound in other substance. Okay, this is the speed of sound in air, and that's what we're talking about. So I'll ask you just a question. Do you think that sound travels faster in air, or in water, or in a solid, like wood or metal or something that's hard? What do you think? Well, just first thinking, you think, oh, air, or at least that's me. And then I think, oh, well, I don't know. Well, look at your table or your chart on 351, page 351, 14.1 table. The speed of sound in certain substances. Okay, we have air, the substance is air, and it's 25 degrees Celsius. Now we should just check them out. And they said it's 346 meters per second. Okay, let's just check them out. 346 meters per second is what they said. So if we did it in 331.5, and we should multiply 0.6, and what was the Celsius temperature? 25, that's right. 0.6 times, let's put 0.6 times 25 right here. We're supposed to add these two together then. 5 sixes is 30, 2 sixes is 12, 13, 14, 15. 15. Now that means I come over here and I add 15.56, 346.5. What'd they say in the book? Air at 25, 346. Uh-oh, they must have dropped the decimal. So they said this here, the exact answers. I don't know why they didn't round it to 347. I don't know. They said 346. This must have been what scientists figured out. Maybe if you would look technically, real technically, maybe it'd have been just a little bit below that. I don't know. But what I'm telling you is they figured correctly. Now you see how I did that, how simple that was? It wasn't hard to figure that. It's not hard for you to do it, but you will need to do it on test. Oh, there, I told you. I wasn't going to tell you that. All right, now, back to my original question. Does sound go faster in air, faster in water, or faster in a solid? Well, look at the next one. Alcohol. I don't know why you put have sound travel through alcohol, but yeah, alcohol, it goes 1,186 meters per second. You get that? That's pretty fast, I can tell you. Woo! 1,000 meters per second. Now we turn over and just look at fresh water. It goes 1,400 in fresh water. So obviously, it travels faster in water than it does in air. Wow. By now you're kind of getting the idea, aren't you? What's it going to do in a solid? We'll just look down the next chart. Wood, steel, aluminum, iron, and glass. Now, we're going to go to the extreme, okay? In glass, sound travels at 5,503 meters per second. Now, I didn't do the math, but if you're going to go 39 inches in a meter, I'm guessing, or 3 foot, just roughly 3 foot, I'm telling you that sound isn't going to quite travel a mile every second in glass, but it's going to get pretty close. 5,000 times 3. No, it would faster than that. That'd be 15,000 feet in 1 second. I can't imagine the speed of sound. So, in other words, reverse this here so you get this well. I want you to understand this. Sound goes the fastest in a solid, the next is in a liquid, and last it's slow in air. Or a gas. Scientists refer to it as gas. All right, now that we've discussed that table, that's important, okay? I'm telling you, you need to get this concept in your mind, and that concept that sound goes slow in air compared to a liquid or a solid. Now let's talk about air again. Let's talk about air, how fast measuring sound in air. The next word that's underlined is supersonic speed. You know those underlined words are vocabulary words on study guide, and they're also on your test. Supersonic, that's pretty easy. You boys should all know about supersonic jets. So, I don't keep up with this, okay, so it's not important, but I do know about the Mach number. The Mach number. You have the black word, and it's pronounced M-A-H-K, Mach. So the Mach number is, Mach 1 is the speed of sound in air. So that's this speed right here, 346 meters per second. M-A-H-K. S. I guess we could go that way. That's not the proper way to determine, but that's 1 Mach. This would, oh, well, it makes a difference of the temperature, okay? That's at 25. If its temperature was 0, it would be this number right here, 331.5 at 0. So this here is equals 1 Mach. Now, let me just talk about, this is how, turn your page to 352, this is how they rate fast flying planes, is they can go 1.5 Mach or 1.8 Mach. It says that NASA has a space shuttle. As a space shuttle comes back into orbit out of space, it's flying at, can you imagine, 10 Mach, 10 times the speed of sound as it comes down. And that's the reason, like, what was it, Discovery, which one of them exploded on the way back when it was coming back? It was traveling so fast, it had lost one of its plates on the bottom in takeoff, and it got too hot. It was just traveling too fast and it exploded. That is because it's speed. Let me talk about this. Whenever a plane, you have the next word there on 352, it's sonic boom. I don't know if you see much of it or not anymore. Maybe you can remember, but I can well remember as a boy that there used to be these low flying jets that would come across our place, and you could hear the sound back there, but the jet would be up here. So if you actually watched and you could hear the sound, you knew, okay, look ahead, because the jet was going faster than the sound, and it was connected with crane, or so I was told anyhow. I don't see many of those today. I don't know, did they stop practicing or they stop flying them? But those jets were flying faster than sound, and so their sound was following them way behind, and they was up ahead. If I'm not wrong, that sound is, and it doesn't say it here in the book, and I was going to check it before I started class and I forgot. I think that you have to fly over 600 miles per hour to break the sound barrier, the way they call it, or to make that supersonic boom. Look how this, 14.5 on your figure there, you have the jet and how it's traveling and the sound waves are going out. And this is a real good example of how this works. So the sound waves are going out and the jet's in the middle. So your first figure, the jet's in the middle. Now the jet's speeding up and the sound waves aren't able to go out in front of him anymore, but they're going out the back, okay? And then finally he pierces his nose through that sound wave. He gets him all piled up in front, and when he pierces it through that sound wave and they can't keep up, it makes a cone shape. Now you're at figure 3, and boom, it goes. I've never heard it myself, but I have told that it will just rattle buildings. It will break out windows in houses. It's just like a serious thunderclap. And it says that most of the time jets that do break the sound barrier will break it over the ocean, so it doesn't damage buildings or hurt your ears. It would damage your ears as well. Okay. Let me see here. Let's keep going here on 352. It's talking about wavelength and sound. So I'm going to erase a little bit here and talk just a little bit how the wavelength and the sound go together. I guess we'll let that wavelength on there with that Hertz symbol, that Greek symbol of Hertz. On 352 it says when a wavelength is large, frequency is small, and vice versa. When a wavelength is large, okay, so it's like this in here starts out, and then it goes down, and it's large. So you're from here to here. When that wavelength is long, can you see there? It's from each side of me there. When it's long, the frequency is small, and vice versa. When this wavelength is tall and short, it's high. That's pretty simple. The frequency is high, and so let me talk about the frequency just a little bit. You got another experiment, and so you do that experiment. That's a pretty easy one to do. It doesn't take a lot. But let me just talk about this here a little bit. When you're in this, when the wavelength is high and short, it's a shriek. It's kind of like little girls screaming. Now I know big girls don't scream anymore, but it's high. It hurts your ears. At least old men like me. It hurts my ears when little girls scream. Yeah, boys don't scream. Yeah, but then when you have a long wavelength like my bottom one here, that's a low sound like a bullfrog. That's a long wavelength. Okay? He isn't tall, he's pretty flat, and he's just a long distance. Where here in this high one, that thing can go up and down 10 times than the bullfrog. And when those girls scream, oh man, that is a high one. So now on 354, if you look, there's some black words almost down at the bottom of the page. It's just real little, and that's key, okay? And I want you to get that because that helps you understand the bullfrog or the high scream. It is this. Sound waves with low pitch have low frequency. And sound waves with high pitch have high frequency. And here again, I imagine Mr. Lau is talking to you about that. You should understand that. Long wavelengths, low pitch, low. And high, short. Yeah, I think that's about all I have for that. I want you, one more thing though. I want you to go over and look on page 355 in the last paragraph. It talks about how that we can detect different sounds or different wavelengths as high and low. And it says that middle C, okay? I know Mr. Lau has taught you where middle C is, and you blow it on the pitch pipe. How many hertz do you think? What's the frequency of that? Okay, you go about halfway. The musical note in which we, the last paragraph, I'm on page 355, the last paragraph before you do your work on your own. The middle C, for example, has a frequency of 264 hertz. Now that means 264 sound waves hit your ear every second. Waves of frequency higher than 20,000 hertz are called ultrasonic waves, and waves with frequency below 20 hertz are called infrasonic, if I can say it, waves. The only difference between the waves is their frequency. Okay, it's how fast they hit. That's the only difference in ultrasonic and infrasonic waves. Now, yeah, I don't know if that's so important that you know that more than it talks about bats being able to hear one. Human ears can just hear a certain amount of them. A certain frequency you cannot hear. Matter of fact, there's very high frequencies, very high sounds I personally can't hear that I used to be able to hear. And that's because I'm advancing in years. Yeah, if you have any questions, give me a call. We will do over to 14.8 questions on your own. You do 14.7, 14.8. You'll actually do 2 lessons. And then tomorrow we'll do a couple more, yeah. So today you'll do from page 351 to 355. I should maybe write that on there so you can see. 351 to 355, and that's in your textbook. I don't know what it is in your workbook. And again, if you did any of those experiments, you call me and I will give you some, I won't tell you what. You call or text me and I'll let you know what privilege you get for doing the experiment. And I may do this again, who knows.